Good afternoon. Um, I hope everyone's had lunch and are still awake. We are here to provide an update on the OCP's test and validation efforts. I'm really excited to be here with my colleagues, Daniel Alvarez and Dan Frame. So last year, several OCP member companies with an interest in data center hardware testing got together to solve a common problem, which is to create portable hardware diagnostics that can work across multiple environments and provide a rich set of standardized result data. And a quick recap, via the problems that we are solving. These include reuse of Diag development and integration efforts, diagnostic portability across multiple products, environments, and use cases. Reproduction of test and validation issues across multiple partners is of particular interest and importance to us, and a way to simply share component vendor tests to accelerate RMA and root cause analysis. And now it's time to check if you're in the right room. OCP test and validation is for you if you are dealing with any of these use cases, which is providing hardware and tests for your data center partners, or developing diagnostic and tests for L6, L10 testing, or you're simply working on product design and qualification, or you're developing software, analytics, and dashboards used for product quality. And if you're interested in data analytics on test data in manufacturing and data center operations, we are certainly for you. And with that, I would like to hand it over to Dan.
Yeah, so this is a quick overview of one of the things that we presented last year. We've talked about data and how important that is from diagnostics, but we had another problem at Google, and that was portability of our test. This is an example of what our test actually looked like. When we build our software, everything runs on a system called Borg. It runs in the cloud, and it's all very tightly integrated and tied together. So when we rolled these things out to either a validation lab or a vendor or maybe our manufacturing, we had a test executive. This thing was coupled together with all kinds of web services that talked to this diagnostics as a service daemon. And this handled all these RPC messages over to job handlers, and these job handlers ultimately invoked our diagnostics. So we had this big giant IT project, but the only thing anybody really wanted was our test. And the OCP diagnostics, it's allowed us to decouple those tests from all the infrastructure and still get all the rich control and information out of those diagnostics while being able to make them much, much more shareable than they were. So now we're at a situation that looks like this. We have a set of common diagnostics. There's about 80 of them right now, and they can run from any test executive. Today we have support for OpenTap, which is a test executive from Keysight. We have support for two proprietary test executives that we use at Google. One's called OpenTest and one's called Burn-In. We also have support for Contest, which you saw during the OCP firmware and open source firmware testing presentation. And then finally, we have Fava, which is a manufacturing test executive that Meta uses. All of these run the same diagnostics. They churn the information into the shape they need, but all the tests are portable across all those different environments. So what is the test executive and what is the OCP diagnostic? We're not trying to come for your test executive, so we know that that's a battle we're not going to win, right? So the test executive basically provides sequencing for the test. It typically integrates with a product lifecycle management system or a control system. This might be an MES system in a factory. It might be a repair system in a data center. It records test results, generally to some kind of persistent store or database. It controls and provides the arguments to the diagnostic to tell it how to run. It may also control the life cycle of that diagnostic, how long to run. It may also be responsible for installing that diagnostic payload on the machine under test. And typically, we let the test executive have the final determination of pass or fail. On the OCP diagnostic side, it's a lot simpler. Its main job is to actually perform the test, whether that be on or off the device. It also handles taking all the input arguments that determine how to control the Diag in a standard way, and then providing that output information in a consistent, streamable format. Finally, it provides pass and fail information as well, but we may override that from the test executive. So at this point, I want to turn it over to Daniel, and he's going to talk about all the different components that make up the OCP Core Diagnostic Library.
So in order to standardize on these diagnostics, we have to align on a number of aspects, including the data model. What information do those diagnostics take in, and what information do they produce, the output that is produced by them? We have to align on how to communicate with them, and this is across many different areas, such as manufacturing, the data center, where we might have different security requirements to connect to the devices under test. We might have different ways of communicating with them, such as SSH or Telnet. So we have to abstract all of those communication methods. We have to have a hardware abstraction interface so that we are able to refer to components within those devices under test the same way, no matter where they are. So we have a consistent way of referring to through within those DUTs. Out of all of these, we saw that the most impact would be had by having a common output data format, and that is what we have focused on first. So the rest of the presentation is going to be focused on the output data format. We will be working on the other aspects as we move on. What are the objectives that we were looking for in this output specification? So first of all, we needed to be standardized so that we have a consistent format that we can use across all our different use cases. We need it to be structured so that it can be later post-processed, as you were seeing in the presentation that preceded us. We needed to be portable. We needed to be able to be read everywhere without specialized tooling. So we wanted to be easily readable and adhering to standards. We need it to be extensible so that it can cater to use cases that we might not have considered yet, or use cases that might emerge in the future. So we leave that door open to be able to extend the current format within its design. And we need it to be streamable. We have, as we were saying, many different use cases. Some of them might run for seconds. A test might finish immediately, or it might run for days or even weeks. If there is a test that is running for a long time, we need that test to produce whatever data it can before it fails. If at any point during that test run there is a failure, we want to be able to use whatever information was produced before the test failed. So that is why we want to stream those results as they are generated rather than waiting for the end of the test. Why is it important that we have this output specification? So it allows us to reuse the test across multiple environments, which reduces costs both for initial development as well as sustaining costs. It gives us a rich data model, which allows for post-processing of the information that is gathered during the test. And you saw good examples of that in the previous presentation. If you weren't here for that, Dan will allude to some of those in a later on slide. It allows us to share component data from the different components that we use at the data center with the vendors in case of failures, and that allows for use cases that we hadn't even contemplated before, such as advanced RMAs. We are able to produce those test results. We send those test results to the vendor, and the vendor doesn't even need for us to ship the failed unit to them. They're able to authorize the RMA because they're familiar with the output format. They know how to understand that, process it, and allow those RMAs in advance. And they allow off-the-shelf tests for common components that are not differentiated. We don't have to reinvent the wheel every time that we have a new component, and we have to develop a new test for it. An example of sharing this information with our partners, our vendors. So many times at hyperscalers, we operate at immense scales. And so even problems that occur relatively infrequently at the immense scales that we are operating at will occur a good number of times. And in order to gather the data for the vendor of the failed part, we many times have to bring up whole IT projects in order to gather that data, to process that data, so that the vendor can ingest it, and in order to help the vendor understand all of that data that we have gathered. Having this common format that we can now share with the vendor and that the vendor understands allows us to much more easily process these projects of processing failed components at the data center. I'm going to hand it back to Arun now.
segueing from what Daniel just spoke about, some of the examples are to safely share that information from the data center to the vendors, including DIM failure and test information at hyperscale, and MTTF and MTDL statistics. This also drives the OCP CI, which offers members and the public firmware testing and validation based on real hardware execution. I hope some of you had the chance to attend the workshop earlier today. And it also enables sharing of frameworks and reproduction of issues between the various stakeholders. An example of this is the integration with Meta's contest framework. Also, thanks to the specification, it's easier to have a community repository of tests. And with that, I hand it back to Dan.
So we've talked about test coverage a little bit already, but in the previous talk, we talked about test coverage in the data center. When we get to manufacturing and design validation, test coverage can be a little bit different. And the OCP diagnostic format, particularly the new version of it, which is 2.0, really lends itself to all different levels. In the data center, when we tie test results, we're generally interested in tying them back to a field replaceable unit, something that a technician can swap. However, when you're in manufacturing, if you have a soldering iron and a BGA rework table, everything's field replaceable unit. There, we're looking at subcomponents or chip level. And then finally, when we do design validation, we can take the coverage for some diagnostics all the way down to the net list, the functional block, or the bus, or sometimes a logical function inside of an ASIC. I've got to go over here and click this button. I missed my clicker. I feel like a caveman. So in addition to that, we've talked a little bit about statistical process control and repair prediction. But really what we get here is anomaly detection of quality and yield problems, predictions of failures, predictions of repairs, cross correlations between processes and parameters, and automatic alerting when we need it. On the statistical process side, we have basically real-time monitoring of key performance indicators. We can watch how they change across time or change over units under test. We can detect product quality problems, and we can also do traditional CP, CPK analysis. The other thing I want to talk about a little bit is redfish and device connectivity. Inside of our specification, and you'll see when Daniel goes in and talks about some of the messages, they're really about tying the data that we collect back to very specific hardware. And we needed a nomenclature for identifying that hardware, and we didn't want to reinvent the wheel. So we've aligned very closely with the DMTF standard in redfish. This satisfies two needs that we have. One, it provides a consistent name for hardware to reference for repairability strategies. For instance, if we're indicting a disk, we don't want the disk to bounce around to different device names based on, how many devices are populated. And it also gives us topology information. So for instance, here in this diagram, you can see we have a chassis. That chassis has a main board. That main board has a DIM riser, which has many DIMs off of it. If we see a condition where all those DIMs are failing, we may not suspect the DIM. We may suspect the DIM riser. So let's look at a real-world example of how this would look with redfish. So here, there's two pieces of information that's interesting to us. One, it's the OData ID, which is the name for the component, and the link information. The link information tells us how devices are connected. And the other part that we're interested in is the location. And this basically breaks down to two parts. We'll look at the part location primarily. It gives us a location type. Is this a socket? Is it a slot? And it also gives us the service label. The service label typically matches whatever is printed on the silk screen, and that's what the repair technician is going to see. So when we take the link information and the location information, we can put those together and we get a unique string for every device in the system that's under test. And we published a library that's available under GitHub, not the OCP GitHub in this case, but the DMTF GitHub. We call this Ecclesia that puts all this information together, and you're definitely welcome to go and check out the bits there and see how this works. Turn it back over to Daniel.
So Dan was alluding to version 2.0 of the specification. Last year we were presenting version 1.0, and we'd like to give you an overview of what has changed and improved. So first of all, as Dan was just alluding to, we now have hardware information that is much closer aligned to DMTF redfish specifications. We have had a number of naming consistency improvements. So we used to have similar concepts that were referred to as in different ways at different parts of the specification. We have now aligned on those. We have added support for a lot more flexible validators, and we will see some examples of those validators in following slides. We have simplified the measurement schemas and flattened them. We have made improvements in file attachment. If the test generates any other output other than the OCP spec output during its run, we now have flexible ways to add those attachments within the specification. We have improved the capability to refer to not only field replaceable units, but also subcomponents within those field replaceable units, as Dan was alluding to earlier. And as we now have a second version of the specification, we have added versioning information to the output so that the output is able to specify whether it's running on version 1 of the spec or the new version 2. So we keep referring to this output specification. What does this entail? What does it actually mean? Well, the whole output specification is pretty much contained within this slide. It's simple as that. The output is composed of different output artifacts, and each output artifact is one of 3 types. It's either a version, a test run artifact, or a test step artifact. The version is very simple. It's what we were just alluding to. It gives you whether you're outputting version 1 of the spec or version 2. Test run artifact gives high-level information about the test, including the test start, the end, and overall logs and errors. And detailed information is contained within a test step artifact, including measurements, measurement series, diagnosis, etc. All of these use standard JSON types and ISO for date and time, ISO 8601. So it's all standards compliant. It should all look very familiar when you see it. And we're actually going to go over some examples of these. So we're going to see a test run start, a test run end, a measurement, and a diagnosis of what this would look like in a typical test. So here we have exploded this out. We have pretty printed it. This is a test run start message, but remember, this would be contained within one line. And within that line, you have the name of the test that was running, the version, and in this case, we're referring to the version of the test, not the version of the output specification, the command line that it ran with, the parameters that it ran with, including those passed by the command line, or others that might be in a configuration file, for example, and information about the device under test that it is running on, including the software that it has and the hardware. Here is a measurement that might be taken by the test, including the name of the measurement, the unit that the measurement was taken in, hardware info of the component that the measurement is actually measuring, subcomponent information about that hardware, and we can have validators. So in this case, we are checking for fan speed, so we want it to be within a certain range. We can specify that with the validators that we have incorporated now in version 2 of the spec. We also have the value that was actually measured, and we can include flexible metadata into that measurement. Based on those measurements, we can then generate a diagnosis, including the verdict of the diagnosis, what type of diagnosis it is, in this case it passed, human readable methods, hard information about the hardware that diagnosis applies to, and the subcomponent within the hardware that applies to. And finally, once the test is finished, we would have a test run end message, including the status of the test. In this case, it has completed, and the result, which in the example is it passed. So this gives you a little bit of a feel of what those messages are that you can expect from the OCP output specification.
Okay, we'll bring this home with a real-world example. So this is a very simple diagnostic. This is a real test. This is basically a benchmark for memory latency. In this case, there's really 2 test steps, right? We have a single test, which is the memory latency test, that contains the parameters and the DUT info. The DUT info contains all the hardware and software information that we know about the device. There's 2 steps, which are really 2 different tests that we're running here. You have the intranode bandwidth. That's the bandwidth between, the same CPU socket and the internode, right? That's basically the bandwidth across sockets. We're recording 4 observations here, right? 4 measurements. Basically, what is the minimum bandwidth we see on each CPU? And then finally, from those measurements, we make 2 diagnoses, right? You can see here that they're good internode and good intranode bandwidth. And those diagnoses are tied back to the specific hardware infos that we have, in which case here it's CPU 0 and CPU 1. This is a passing test. We would use this to exonerate these components if we were looking at them in a repair strategy. Arun?
So what's next? Well, we're working on diagnostics for CPU, storage performance, peripheral devices, and protocol and memory. So if you were in the right room and are dealing with these use cases, please do consider OCP diagnostic core libraries. Dig in via the repositories and all of the resources that we've highlighted. We look forward to feedback, pull requests, and help to build the vision out. We'd like to thank all of these invaluable members and companies that have contributed to the efforts, including Meta, HP, Keysight, and Google. And so join us. All of the details that you need are out here. And we also have a weekly meeting that happens every Wednesday at 8 a.m. So we look forward to hearing from you all. Thank you.
So if anybody's got any questions, we'll be here along with Richa and you and Lynn if you guys want to talk about repair, diagnostics, anything at all. Thank you guys all very much. I know it's the end of the day on Thursday and it's repairs, and I really appreciate all the attention. Thank you.
Thanks.